Single trees are typically not competitive in terms of predictive accuracy compared to many alternative predictive models. In this video, we introduce the general idea of bagging, boosting, and random forests. Note that bagging and boosting are general ideas that can be applied to many other predictive models as well. When applied to trees, the basic idea is to grow multiple trees which are then combined to yield a single prediction. Combining a large number of trees can often result in dramatic improvements of prediction accuracy at the expense of some loss of interpretation. Bagging, boosting, and random forests are all straightforward to use in software tools. Bagging is a general-purpose procedure for reducing the variance of a predictive model. It is frequently used in the context of trees. Classical statistics suggest that averaging a set of observations reduces variance. For example, for a set of n independent observations, each with variance sigma squared, the variance of the mean of the observations is given by sigma squared divided by n. Therefore, to reduce the variance of a prediction, we can simply average its predictions from multiple datasets. While this is a straightforward idea, it is not practical, since we generally do not have access to multiple training sets. To resolve this issue, we take repeated samples from the training set. This is usually called a bootstrap. We can then train the model on each bootstrap sample and average the result. This procedure is what we call bagging. We can also cross-validate, using data not in the bootstrap samples. Bagging can sometimes significantly improve the predictive performance of trees. Note that from our description here, that bagging is a general idea and can in principle be applied to many other predictive models, such as linear regression and logistic regression. Random forest is similar to bagging. It builds on the idea of bagging but tries to reduce the correlation among models built with different samples. In the context of trees, this is achieved by building trees on random subsets of the predictors. That is, when building trees, we do not use all predictors. Since the trees are not built on the same set of predictors, they are naturally less correlated, and therefore it reduces the variance of the average prediction. The last idea we discussed is boosting. Again, this is a general idea that can be applied to many predictive models. We'll briefly discuss it in the context of trees. Similar to bagging, boosted trees are built on bootstrap datasets. However, the boosted trees are grown sequentially. Given the current model, we fit a tree to the error from the model. Combining the trees can potentially improve predictive performance. Here, we show the cross-validation results for the Boulder housing data. Since this is a regression problem where the target variable list price is continuous, we report a total sum of squared errors on validation data, with a default 60-40 split. For the full tree, the SSE is 6401340. Pruning the tree slightly reduces its error. Building a random forest further reduces its error. More significant improvement is achieved by bagging and boosting, with the lowest cross-validation error reported for boosting, which stands at 53251639. This number is almost 20% lower than the one from the full tree. I comment here that single trees are known to perform poorly in general. Therefore, for practical predictive modeling, we almost always use advanced techniques such as boosting, bagging, random forests that we discussed here. Let me briefly discuss the strengths and weaknesses of tree models. In terms of strengths, trees are easy to understand or versatile. They can be used for both classification and regression. We do not need to worry about variable selection as in linear regression, since variable selection is automatic. There's also no need for variable transformation, which is yet another advantage. It is also known to be robust to outliers and missing value. But trees also suffer from several weaknesses. First, they are only appropriate for large datasets. Second, since trees cannot capture interactions among different predictor variables, they are not good at modeling linear relationships. Third, they are prone to overfitting. Therefore, it's important to cross-validate and prune. Finally, trees do not produce rigorous insights like linear or logistic regression models. Overall, trees are powerful as a predictive model and should be part of a modeler's toolbox.